Hello everyone, I'm Qingzhi. Today I'm going to give a talk about QReg, a query-centric regression for In-DBMS analytics. A new dominating trend has emerged for the data management and analytics based on integrating machine learning models and data management platforms, which includes research for connectors to backend databases, which allows for statistical analysis and related queries on databases, and also approximate query processing like DBS, DeepDB, deep generative models, and also model management and query prediction serving systems like Velox Clippers, and regression being a principal means for predictive analytics is of particular interest to both analysts and data analytics platforms. Currently, many modern databases provide support for regressions, such as the Microsoft SQL Server, the Oracle Server, and academic efforts includes Postgres, MAT, MorphDB, and also UDFs are also used to compute regression models. In the field of database systems, it is widely acknowledged that query workloads follow patterns, generally different to data distributions. However, regression models are generally designed to minimize a global loss function. Thus, if people are interested in a subspace of the dataspace, the error from the regression models would be high. Here is a one-dimensional example for the Beijing PM2.5 dataset from the UCI machine learning repository. We have trained a linear and a polynomial regression model to predict the PM2.5 value for a given cumulated wind speed. As the regression model are trained to minimize a global loss function, both regressions fit the data well. However, if people are interested in the subregion as shown in the blue circle here, then neither regression will work well. So this gives us an idea. If we could combine the strengths of these two regression models and select the most accurate model for a given point, as shown in this figure, the accuracy will improve a lot. Here is another example for the two-dimensional Beijing PM2.5 dataset. The left figure shows the distribution of the best model when linear regression, polynomial regression, and decision tree regression are used. It is clearly shown that the linear regression dominates in the upper central region. Polynomial regression dominates at the lower central region, and the decision tree regression performs best in the rest of the space. The NRMC error are close to 8.5%. If, for each point, the best model can be selected to make the prediction, the overall error drops to 7.2%. This is a large improvement in accuracy. The right figure shows the distribution of best models when ensemble models, XGBoost, and gradient boosting are used, and the same conclusion holds. Thus, given several regression models at hand, if we could always choose the best model to make the prediction for a given query, we could improve the accuracy a lot. We treat this model selection as a classification problem, and this gives rise to QReg, the query-centric regression. This is the system architecture of QReg. There are two layers in total. The query classification layer receives each query and uses a classifier to decide which model will be used to make the prediction. The model maintenance layer maintains several regression models. To train QReg, the dataset is partitioned into three subsets: training dataset 1, dataset 2, and the testing dataset. Training dataset 1 is used to train the best regression models, like linear regression, polynomial regression, and decision tree regression. And the training dataset 2 is used to train the classifier. The testing dataset is used to evaluate the accuracy of QReg. Firstly, best models are trained on the training dataset 1, and predictions are made for points in training dataset 2. Then we could compare the accuracy and find the best model for each point in training dataset 2. So now, each point in training dataset 2, along with the index of the best model, forms the new dataset, which is further used to build the classifier in QReg. Here we talk about the experimental setup of QReg. There are two configurations of QReg. Simple QReg use linear regression, polynomial regression, and decision tree regression as the best models. Advanced QReg use ensemble models, including XGBoost and gradient boosting as its best models. To evaluate the accuracy performance, the normalized root mean square error, or NRMSE, is used. It provides a universal measure of predicted accuracy between different regression models. The NRMSE ratio here shows how worse regression model I is compared to regression model J. And we defined opportunity loss, which quantifies as a percent error due to not using the best model, but using regression model I instead. We further define the relative opportunity loss, which quantifies how much better regression model I does versus regression model K in improving the opportunity loss. Now let's see the distribution of best models obtained by QReg for the Beijing PM2.5 dataset. The top two figures shows the distribution of the best models, which is the ground truth, and the bottom two figures shows the distribution of best models obtained by QReg. It is clearly shown that the model distribution resembles the distribution of the truly optimal models across the query space. Now let's have a look at the accuracy for simple QReg. Simple QReg uses linear regression, polynomial regression, and a decision tree as its regression models, and we compare the accuracy between a single model and QReg. It is clearly showing that the NMSE ratio is greater than 1 for all datasets and for all regression models. This means QReg has better accuracy than any of the regression models. We further compare the accuracy of simple QReg against other ensemble methods, including AdaBoost, XGBoost, and gradient boosting. It is clearly showing that simple QReg often achieves better accuracy than any of the ensemble methods. For example, up to 25% reduction in error is achieved by simple QReg for dataset 1 in the 3D space. Here we show the accuracy performance of advanced QReg from a different perspective. Take Figure B as an example, and now we are interested in the collection of points where XGBoost has the best accuracy. Then we could compare the accuracy between QReg and gradient boosting for such collection of points. Take dataset 1 as an example. Gradient boosting suffers from 32% error relative to the optimal model, while using QReg reduces this to 7.8%. The relative opportunity loss is 4.2, which means the error cost by using gradient boosting is 4 times the error cost by QReg. As a query-centric regression, QReg must be able to handle large amount of data. The left figure shows the training time as the number of training points increases. There exists an approximate linear relationship between the model training time and the number of training points. This limits its application to very large datasets. An approach to addressing this problem is to build samples from the data and train QReg on samples. Reservoir sampling is used to generate uniform random samples. The store sales table from the TPCDS dataset contains more than 100 million records. To make a random samples, it takes around 1 minute. Here we show the accuracy performance of QReg based on samples. Similarly, using QReg reduces the error a lot compared to the other regression model. Here we apply QReg to DBS, the state-of-the-art model-based AQP engine. It uses regression models and density estimators to provide approximate answers to SQL queries. The default regression model XGBoost is replaced with advanced QReg, and the figure shows the reduction in accuracy if advanced QReg is used for aggregate functions sum and average. For sum, the relative error using XGBoost or gradient boosting are 8.35% and 8.1%. However, if advanced QReg is used, the relative error drops to 7.7%. The overall error is also reduced using QReg. So in conclusion, different regression models are better performing for different datasets and, more interestingly, for different data subspecies within them. And best practice, which suggests using a top-performing ensemble, is misleading and leads to significant errors for a large number of queries. A query-centric perspective, as manifested with QReg, can offer higher accuracy across datasets and dimensionalities. This applies to overall in-MSEs. More importantly, it applies to query-centric evaluations. Accuracy improvements are achieved with small overheads, even with very large datasets, using samplings. That's all. Thank you.